Unit 5 Writing Classes, Topic 5.6 Writing Methods. This is a basic UML diagram of a class. Again, you should be comfortable drawing these to help you construct code for FRQ Style 2 questions. We've gone over writing the header of a class, declaring private instance variables, defining default and overloaded constructors used to initialize the instance variables. Most recently, we focused on defining non-void accessor methods, or getters, along with void mutator methods, also known as setters. In this lesson, we will look at writing other methods and behaviors along with their characteristics. Let's do a quick recap on calling methods from Unit 2, Topics 2.3, 2.4, and 2.5. There are 5 parts to consider when writing a method signature. The accessor modifier needs to be set to public or private. Ownership needs to be determined. Will the method be a static method in which the class owns the method, or non-static where the object owns the method? Ownership determines what gets to call the method. The math class methods are mostly static, which is why they are called through the class. In the second example, bark is a non-static method that is called on an object dog. You then have to consider the return type. The data type of the value to be returned by the method can be primitive, reference, or void when no value is returned. You will then need to name your method. That name is also called an identifier. It should be meaningful so that the method's purpose can be easily identified. Following the identifier, you will have a parameter list which will be enclosed in parentheses. Even if you don't have parameters, you still need the parentheses. Parentheses make it easy to spot methods in code. Here are some examples of void methods that do not return values. Here are some examples of non-void methods that return values. Why do we create multiple methods? For organization and reducing complexity. We can divide a problem into subproblems to solve it a piece at a time. It's helpful for reusing code. It avoids repetition of code by reusing code and calling it whenever needed. We also do so for maintainability and debugging. Smaller methods are easier to debug and understand. Methods can only access the private data and methods of a parameter that is a reference to an object when the parameter is the same type as the method's enclosing class. Let's look at an example. Consider software developed to handle running a dog competition. Since the software would need to contain information about multiple dogs, we would want to have a class to handle the data and behavior of a dog. The dog class would be separate from the class that manages the competition. Let's start by encapsulating or protecting attributes and behaviors of a class. Here we are defining a dog class with a private instance variable called breed and an accessor method called getBreed. Let's add behaviors or methods in another class. The results of one of the events in the competition involves a match between 2 dogs, and the outcome depends partially on whether the dogs are of the same breed. This method could be implemented in the dog competition class or in the dog class. Let's first consider how it would look like in the dog competition class, outside of the dog class. Notice that this is another class called dog competition, and the method doBreedsMatch will check values of dog class objects. It is important to observe that the objects dog1 and dog2 have private instance variables that cannot be directly accessed outside of the dog class. Accessor methods, getBreed, allow us to safely access the private instance variables of these objects. What if we decided to write this method in the same class as a dog class? Even though breed is private data in the dog class, we can access it directly as we are in the dog class. So both the calling object and the parameter can access the private data. A great question to ask ourselves as we trace code is, where are we? Am I in the class that gives me direct access to private instance variables, or am I outside the class that will require the use of an accessor or mutator method? Non-void methods with parameters receive values through parameters, use those values, and return a computed value of that specified type. Let's practice. Complete the code. Consider the following partial class declaration. Which of the following is a correct replacement for the missing code to update the isFrosted data member of the calling object to match the parameter's isFrosted value? It is good practice to start by asking yourself, am I inside or outside the defining class? If you're inside, you can access the private instance variables directly. If you're outside, you will need an accessor method to access the private instance variables. In this case, you are inside the cake class. You can call the private instance variable isFrosted directly. There is also no problem of using the getIsFrosted method. Now here's a common mistake. Accessor methods cannot be assigned values, so this third option is incorrect. Let's complete this code. Now consider a class that uses cake objects. This class is outside the cake class and it's called bakery. Each cake used 5 cups of frosting if it was frosted. Which of the following is the correct replacement for missing code 1 and missing code 2 so the method works as described? Remember, we are outside the cake class as we are viewing the bakery class. Because of this, we cannot directly access cake instance variables directly. We must use the accessor methods to do so. It is good programming practice to not modify mutable objects that are passed as parameters unless required in the specification. Let's do a quick recap on parameters. This is the parameter list. It is contained within the parentheses. When declaring or defining methods, these are called formal parameters. When calling the method, these parameters are called actual parameters as they are the actual values to be assigned to the object. They must be of the same data type and in the same order as the formal parameters. We're going to look at how our computers or machines process parameters. We will look at how parameters that consist of primitive types are processed, and then we will look at how parameters that consist of reference types are processed. When an actual parameter is a primitive value, the formal parameter is initialized with a copy of that value. Changes to the formal parameter have no effect on the corresponding actual parameter. Take a look at this example. In the first box, we're declaring a method and assigning it formal parameters, and in the second visual, we have the actual parameters being placed. Notice that the original value is unchanged after being used as a parameter. Let's practice. Take a look at this code where primitive values are set as parameters. What is the output when the program is executed? Create a trace table to verify your answer. At the start of the program, I've initialized the variable x to 33. My next line of code is going to call the method increment parameters, passing the x value as a parameter. X will now become the actual values in this method. A will be replaced with 33. A is going to be incremented and become 34. I will then ask to print A. Notice, A will change to 34, but X is still 33. When the method is called and X is passed as a parameter, the original value of X is not altered. At the end of my program, I should see the values 34 and 33. When an actual parameter is a reference to an object, the formal parameter is initialized with a copy of that reference, not a copy of the object. If the reference is to a mutable object, the method or constructor can use this reference to alter the state of the object. Passing a reference parameter results in the formal parameter and the actual parameter being aliases. They both refer to or point to the same object. Let's look at an example. On the left, I have a method called resetRectangle, which will take in a rectangle object as a parameter. And in the next box, we'll look at examples with actual parameters. Notice that the original value is altered after being used as a parameter. This is different than how primitive values are used. The reference variable changes because the formal parameter is an alias of the actual parameter. Let's practice. Here's an example using reference types as parameters. We have a public class called mutable. It has a private instance variable called value. It has a constructor. It has a method called increment value, which is a mutator method. Because of this, an instance or an object of this class can be considered mutable as it contains this method. There's also an accessor method in this class. Look at this code. What is the output when the program is executed? Here's the class again for your reference. How might you visualize this using reference types that point to data? Let's look at our code. Let's start by instantiating an object X of type mutable that has the parameter 33. Notice at the bottom how we're visualizing this. X points to the reference that stores the value 33. I then call the increment parameter passing the X object. Notice that X is still pointing to the reference that's storing the value 33. When this method is called, my computer is going to go find the method and pass actual values into the parameters. Now I have another object, A, that points to the same reference as X. These two are considered aliases. I will then call the method increment value, and the value that's being stored or referenced now changes to 34. Because this is a copy of the reference, x is now pointing to the value 34 just as a is. How is this different from the previous example when we were passing primitive values?